Hi, everyone. Happy Wednesday. Thank you for joining us for today's webinar on navigating the myriad of rainscreen cladding attachment systems. I have Len here with Exo-Tec that will be leading today's AIA-approved presentation. A few things before we get into the presentation here while I wait for everyone to join. Like I said, it is AIA approved. So once the presentation gets going, I will drop a link in the chat just in case you didn't sign up with your registration number so you can receive credit for today's presentation. The next thing to note here, we'll be doing a webinar poll about 3/4 of the way. This is a great way to connect with Len after today's presentation and request things like product literature, technical installation information, price quotes, samples, etc. And the very final thing I want to note is where you can connect with Len and find their brand page. So I'm quickly going to share my screen here. This will be the second link I drop in the chat. This is a really great way to find out more about Exo-Tec's products. And then you can click on this button right here, contact, and that's how you'll directly get in contact with Len through Acelab's platform. Okay, so I'm going to stop sharing our screen here. And I think that is it on my end. If you have any questions, feel free to drop them in the Q&A. We'll get to them after today's presentation directly through email or some other form of communication. Thank you so much.
Thank you everybody for attending. Appreciate it. I own the Exo-Tec companies. I have Exo-Tec Manufacturing, which manufactures some products I invent to try to solve problems in the industry, and Exo-Tec Solutions, which is an independent rep firm in the New England area, and also Exo-Tec Consulting. I do, my specialty is building enclosure. I do consulting for architects, engineers, building owners, building managers. A lot of what I do is hydrothermal analysis using the WFI program. As you can see on the screen, I'm WFI certified and WFI advanced certified. There we go. As mentioned, we are offering AIA credits through the Air Barrier Association of America. I was a founding member of the Air Barrier Association. I actually incorporated it. I was president for its first 2 years, and then or vice president for the first 2 years and president for the next 8 years until we got air barriers into the International Energy Conservation Code. And during that time, I noticed that once the code changed, the industry changed a bit, and a lot of manufacturers jumped into the air barrier market with all sorts of different products and claims and whatnots. And it took a good decade to sort through it all and get rid of the bad products, change the codes for a better air barrier system. So I put this presentation together to try to weed through everything that's out there on the market. Restart the. Okay, so what I did is I have a little bit of OCD. So one night, I had a lot of my architectural clients sending me cladding attachment systems after the continuous Z-furring was ruled out by the code. And I'd say, well, yeah, this does this, but it doesn't do that, and it does that, but it doesn't do this. So for my consulting, I sat down in one night and just sat there for hours, and I compiled a list of what you need for a rainscreen cladding attachment system. This was my wish list. So it has to, number one, it has to withstand the loads imposed on it, and I'm happy to report they all do. It has to comply with IBC and IECC requirements. There are many out there that don't. It can't burn. This is your non-combustible, your requirement for your non-combustible constructions, which is types 1 through 4. Results in minimal thermal bridging through the continuous insulation. So if it can't burn, it's probably going to be metal. Since metal is a thermal bridge, there's a definition for it. I'll show you. what's allowed, but you want to minimize the amount of metal in the system that passes through the insulation. I want it to install easily with few parts to assemble. I want it to provide the required adjustability without having to shim because shimming takes time um, and extra cost to buy the shim. I want the cost to be reasonable. The costs right now are anywhere from say $3 a square foot up to like 11.50 a square foot. So there's a big range on cost. And I didn't want it to require cutting and fitting of the continuous insulation because that's just going to take a lot of labor to do that. I didn't want it to require shop drawings. We didn't need shop drawings when we're using continuous Z-furring. So if we don't have to submit them, the work to do them, submit them, review them, approve them, it's going to save some time. And one thing that was really important to me coming from the Air Barrier Association of America is that it provides mechanical fastening for the continuous insulation. If it doesn't have this, then you have to put fasteners through, which puts holes in your air barrier. I'll get into that a little bit more later. All right, so let's look at the IBC code requirements. There's non-combustibility requirements and fire rating requirements for load-bearing members and other components in the exterior wall assembly. So 602.2 states for types 1 and 2 construction, the building elements listed in table 601 are of non-combustible materials. Type 3 construction, it says exterior walls are of non-combustible materials. Your type 4 construction, this is your heavy timber construction. They have to be non-combustible materials. As you know, heavy timber, once it starts to burn, it chars on the outside and that protects it. And type 5 construction, you can use any type of material in there, combustible materials. So Chapter 7 of the code states that load-bearing structural members within exterior walls or on the outside of the structure shall be provided with the highest fire ratings as determined in accordance with Table 601 and Table 705.5. So your cladding attachment system is a load-bearing element. It's going to bear the gravity load of your cladding system, and it's also going to transfer the compression and suction wind loads to the structure. So looking at table 601, you can see for exterior bearing walls, there's fire rating requirements here. So on top of being non-combustible, but type 2B, you don't need a requirement, and type 5B, you don't need a fire rating, any fire rating on there. For non-bearing exterior walls, I refer you to table 705.5. And here's 705.5. This is basically your fire separation distance chart, depending on how far apart you are from the building next to you. If it's less than 5 feet, there's a top line. You need 3, 2, and 1 based on occupancy. 5 to 10 feet, 10 to 30 feet, and above 30 feet, it doesn't require a fire rating of that wall. So a lot of manufacturers out there, a good handful of manufacturers are using fiber reinforced polymers or FRPs. When I was growing up, we called this fiberglass, but now there's different reinforcings other than glass as carbon fiber and some other ones. And they say theirs meets the code because in chapter 26 of the code, 2613, it said the fiber reinforced polymer should not exceed an aggregate total of 20% of the area to which it is attached. Single architectural lines should not exceed 10% of the area specific to the wall which is attached. And no contiguous sets of architectural elements shall not exceed 10% of the area. In my opinion, and that of many experts in the business, this is for architectural features. It even says architectural elements. This is for like trims and et cetera that are attached to the veneer of the building. I don't think this refers to the cladding attachment system. So I don't think this argument holds water. The other argument I get a lot, or the other statement I get, or argument for FRPs is, oh, our product passed NFPA 285. And I have to remind them that NFPA 285 is not a product test. It is an assembly test that evaluates an assembly for fire propagation characteristics of the exterior non-load bearing wall assemblies. It is only a 30-minute burn, so there's no way that you can get a fire rating off of this. And there's only two failure criteria, and that's flame propagation and temperature exceedance. So the flame can't spread vertically above the window opening more than 10 feet, and it can't spread laterally more than 5 feet on either side of the window opening in the assembly. The exterior facade temperature, if it exceeds 1,000 degrees, it fails. Um, you'll see, I'll show you later that a lot of these FRPs burn at 1,000 degrees, but more importantly, they melt at a much lesser temperature. The temperature within the assembly can't exceed 750 degrees, and the temperature in the room, the second story room, can't exceed 500 degrees. So this is all the failure criteria um, that NFPA 285 requires. So just a quick recap, it's a 30-minute burn. It tests for fire propagation. The failure criteria is flame spread and heat generated. Rain screen cladding panels falling off the test panel does not constitute a failure. And this is something that a lot of people have presented to or talked to. This, like I said, this is not a fire rating test. Here's the test itself. I got to witness it down at Intertech in San Antonio. It's a violent test. We were standing about 50 feet back, and I thought my clothes were going to start to melt off. Uh, just a 3D of what the test is they have a burn room with a burn bar in there. They light that on fire, and after so many minutes, they have a cart on wheels with a burn bar. They light that on fire. They roll it up, and they burn it for 30 minutes. And if any of those criteria are hit, flame spread or temperature uh, achieved, then it's considered a failure. The other argument I get a lot for FRPs is, oh, well, we're class 1 fire rating under ASTM 84. ASTM 84, known as the Steiner tunnel test or the tunnel burn test, that's to evaluate surface burning characteristics of materials. It's not a fire rating test, it's a fire propagation test. So it's testing how fast that product burns. There's only two key metrics in ASTM E84. One is the flame spread index, and one is smoke develop index. So for your flame spread, your class A or class 1, this is where they say it's a fire rating. It's not a fire rating, it's a burn rating, is 0 to 25. Class B or class 2 is 26 to 75, and class C or class 3 is 76 to 200. For all classes, the smoke develop index is 450 or less. Let me just go back here. So just the flame spread, it's a barometer is red oak, which is 100, and then cement board is 0. So because cement board doesn't burn. So basically, this test was to assess how materials behave in the early stages of a fire, and it's commonly applied to interior finishes like wall covering, ceiling tile, flooring to determine their suitability for use in specific occupancies based on their fire hazard potential. Um, Another claim that some of these manufacturers make is say, oh, well, we've added a flame suppressing additive to it. And I have a product called GMX that I invented. It's used for spray foam stop. If you're doing spray foam and you come up to a door or window perimeter, you put this up instead of trying to square it off or putting wood there or having someone stand there holding a spray stop. In I think it was about 2013, 2014, when everybody jumped on the E84 bandwagon for exterior wall elements, I had to add this to be able to pass the E84 to get a Class A rating. And as you can see, it still burns. But once you take the flame away, the self-extinguishing additive puts the fire out. But in a building fire, the fire doesn't just turn off. So we can see it goes out, but it still burns. All right, let's look at the IECC code requirements now for exterior wall assemblies. You have wall assembly U values. There's performance requirements and prescriptive requirements. I like to stick with the performance requirements. I don't agree with the table and the prescriptive requirements. I think that under the many conditions that you can have a failure of that wall assembly hydrothermally, and then they define continuous insulation. So here's your performance requirements. I'm in zone 5 here. So for metal frame building, my exterior wall assembly, the whole assembly has to have a U factor of 0.055. So what does that mean? And I know a lot of people don't identify with the U factor as well as the R value. So if you take the U factor for metal framed exterior wall in my climate zone, which is U 0.55, the U factor is the inverse of the R value. So if you divide 1 by the U factor, you're going to get R 18.18. Now, that value is determined by ASHRAE 90.1 committee. They review it every 3 years, and based on your climate zone, they do a scalar analysis or cost benefit analysis, and they feel that the R 18.18 or U 0.055 is the optimal insulation value. When you go above it, it starts not being, based on the cost of materials, cost of adding them, and the energy savings. You don't need to go above that. So the other chart that I don't like, the prescriptive requirements that's in the code here, is for metal frame buildings in zone 5, you want R13 insulation and then R10 continuous insulation over the sheathing. And if you have a high humidity building, like I said, I've run a lot of WUFI analysis or hydrothermal analysis. I find that in medium and high humidity environments, that wall assembly fails. There's too much moisture that builds up in that wall. So I like to steer people away from that, designers away from using this table. I'm in Massachusetts in our stretch energy code, which we have 300 of our 366 municipalities have adopted the stretch energy code that says you cannot use this table. And I'm hoping someday that the International Energy Code, Conservation Code Committee will get rid of this table. All right. It also defines continuous insulation, which is insulating material that is continuous across all structural members without thermal bridges other than fasteners and surface openings. So why did they put this in? Because thermal bridging to the continuous insulation needs to be dealt with in order to comply with the performance requirements of the ICC. So finally, we're getting a little bit smarter about our insulation. Instead of just saying more, 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 let's get rid of the thermal bridges through it and just make that insulation more effective. So basically what that does is it gets rid of our continuous Z-furring that we use for a lot of years. So you can't use this anymore in the exterior walls per the definition. And also I'm going to show you that you won't comply with the performance requirements of the code if you do use it. So using a program called Therm, which is a free download from Lawrence Berkeley Laboratories, you can show the effect of the thermal bridging on that continuous insulation here. And basically, you lose 46% of the R value of your continuous insulation. So if you have R10 continuous and have continuous Z-furring at 2 foot on center, you only have R 5.4 for that. So you don't meet the R10 continuous. And what they also did in the code is they put this table in here to penalize your assembly for light gauge metal framing. So for steel studs. So if you take the R13 that they say that you can have inside the stud cavity and you factor in the thermal bridging, that value is only R5.98. So you're R11.38 basically with continuous. If you go R10 continuous and R13, then factor in your thermal bridging, you're only at R11.38, 5.98 plus 5.4. So you're not meeting the performance requirements of the code. That's why I want that other table, the prescriptive table, to be taken out of the code. The other thing we have to consider is their insulation fasteners. The fasteners do create thermal bridges. Every expert that I've talked to when they do thermal modeling say that yes, they do factor in the thermal bridges for the fasteners. But the other thing that bothers me is these fasteners results in thousands of unsealed penetrations through the air, water, and if it's a vapor barrier also. And this is what I see on job sites a lot. When you use these insulation fasteners, you have a hole in your air, water, and vapor barrier here in this particular job. I pressed and pressed the Air Barrier Association to get going on some research. They finally did, trying to come up with a test to see how this affects your air barrier. They did a first round of work on it, and then COVID hit. And we're partnering with um, um, Oak Ridge National Laboratories in Oak Ridge, Tennessee. They were heading it up. And we got through the first round, COVID hit, and now the person who's in charge of it can't fly, so it's kind of dead in the water. I'm still pushing them to finish the whole research project and come up with a test protocol for this. So the 2024 International Energy Code requires the derating of insulation based on the amounts and types of thermal bridges through your continuous insulation layer. This is accomplished by factoring linear thermal bridges and point thermal bridges. And if anybody's done a passive house project on there, passive house does this. They do that already. They've been ahead of the code for a while, and now the code's trying to catch up to what they're doing there. So C402.7 it deals with the thermal bridges and above grade walls, and said you have to comply with this section or approved design. There are some exceptions. In number 4, thermal bridges accounted for in the U factor, C factor for building thermal envelope. This is what passive house does. So for your cladding supports, it says linear thermal elements supporting opaque cladding shall be offset from the structure with attachment that allows the continuous insulation where present to pass behind the cladding support element, except at the point of attachment. There again, they do have the exception for like a passive house, approved design where the above grade wall U factor is calculated for it, and then anchoring the windows. So basically, you have to derate for your linear thermal bridges and your point thermal bridges, and this includes insulation fasteners. They spell out your linear thermal bridges for you, but they don't tell you basically how to do your point thermal bridges. They really don't address it. I don't know why. I've brought this up and people are looking into it. They're trying to get this code cleaned up because it's a bit of a mess right now. So for your linear thermal bridges, you're assigned what's called a psi value, which is this italic trident here. And your point thermal bridges are assigned a chi value, which is a subscript italic X. These are used to calculate the derating of your continuous insulation. And here's the formula you use. This is in the code. I know it looks a bit daunting. Math equations with no numbers usually are. But to get your UD rated, you use this equation. It's actually fairly simple. The epsilon means the sum, and there's your psi sign. So you take the sum of all take your psi value of each linear thermal bridge times the length and sum them all up. And then you add to that the sum of all your chi values or your point thermal bridges times the number of those point thermal bridges. And you divide that by the area of the opaque wall. And you add that number to your U opaque, which is your insulation, your wall with your insulation. And that's going to bump your U factor up, which is going to worsen the performance of it. So it's not that tough to understand once you read into it. So I'll just break this down. For your linear thermal bridges, to get your UD rated, you take your psi value times the length divided by the total area of your opaque wall, and you add that to the U factor of your opaque wall, and you're going to get your D-rated U factor. For your point thermal bridges, again, it's chi value times the number of point thermal bridges divided by the total area of the opaque wall, add that to your U of the opaque wall, and you come up with your D-rated U factor. So in the code, they give us a table 402.1.4. In here, they give you psi factor compliant with section C 402.7 and then non-compliant. So you can use a psi factor. Notice they don't have any chi factor. And let's take a 20,000 square foot building. You'll have about 10,000 linear foot of attachment if you use the linear thermal for your linear thermal attachment or your linear attachment here. So 0.2 times 10,000 feet divided by 20,000 is 0.1 plus 0.0775. You got 0.1775. So that brings your R value down from, if you're using 3-inch mineral, 12.9 to 5.63. So your D rating is 0.436. That's a huge D rating. And when I run these numbers, they don't make any sense to me. If you do the the psi factor of 0.3 for non-compliant, your D rating is 0.338. And these numbers just don't work in the real world. And like I said, I know some people that are working on trying to clean this up. So what you want to do is get 3D thermal model psi and chi values to calculate your D rating factors for your project. So let's look at the systems that are out there on the market right now. You have your FRPs. A lot of them say they are thermally broken. They're not. A thermal break is something that stops the thermal transmittance of that material. So you have to put it in the middle of the material. It does have low thermal bridging though, because it is R.7 for these FRPs. They're few parts, easy to install. You have a seal at the fasteners here where you fasten it to the wall because you have a flat plate that presses into your air, water, and vapor barrier. And you will get a seal if you compress something over it. You don't need shop drawings, and these are the lower end cost materials out on the market. The cons are that it burns. So me and many experts in the industry feel that you can't use this in combustible construction, which is types 1 through 4. In some cases, the insulation fastening is friction fit. There's others that have little clips on it to fasten it or lips to fasten it. I don't like these horizontal orientations as I think they can hold water, especially in this one in the lower right-hand corner. They did put a weep hole in, but it's raised up above the flat surface there. There's no adjustability in these. You're going to have to shim every panel. The maximum spacing is 2 foot. And one manufacturer that has an FRP one, I'll show you that a little bit later. They cite a paper by American Society of Civil Engineers that say if you put a screw through an FRP product, the FRP product will fail because you're breaking up the resins in there. I don't know why they did this because theirs has FRP too, and they put a screw through it. So looking at the FRPs, I did an AI search for FRP burn temperatures. So most of these are polyester resins. So the polyester and vinyl resins, they burn between 662 to 932 degrees. Your epoxy resins, they're going to ignite at 752 to 1022 degrees. So, but they don't really burn. They go through, like wood does, they go through thermal decomposition. They call it pyrolysis. And this is around 572 to 5000 or 752 degrees F for your thermosets, which most of them are a thermoset. I believe all of them are a thermoset. But what's more concerning is in order to make these materials in that profile, they have to get them to a liquid phase. So they have to have they have to melt at a certain temperature, and that melt temperature has to be below the burn temperature. Otherwise, you'll burn the material up. So your thermoplastic FRPs, that melt temperature, so they can get it through the Play-Doh fun factory of life, so to speak, is 392 to 662, depending on the resin. For thermosets, it's 248 to 392 degrees. So it's about half the burn temperature there. So, and it all depends on what's in there. So here's the concerning part. I did an AI search for building fire temperatures. So your early stage temperatures are 212 to 932 degrees F. Fully developed fire is 1102 to 2192 F. Peak temperature about 27, a little over 2700 degrees. These products are going to melt in a building fire, and you're going to have rainscreen panels falling off the building. And I've spoken to several different, people, firemen that I know or friends or whatever. And I said, you guys, when you're fighting a fire, you're not looking up to see if anything's falling off the building, right? And like, no. And I tell them about this, and they're very concerned about it. I know, in the city of Boston, they're looking into it. The Inspectional Service Division is looking into this because they don't want firemen hurt or even killed by these panels falling off the building, or bystanders, or the damage that it can do to vehicles and like fire vehicles and everything. So not only do I interpret the code to say you can't use these, I think just common sense says you don't want to design a building or build a building that's going to have panels falling off of it if the building catches on fire. It's just like a common sense thing. So here's another FRP product, and this one they add. This is the company that says, if you put a screw through the FRP, it will fail. They put some metal in there, but you still have to put a screw through it. Um, so again, this is low thermal bridging. It's R.7, few parts, easy to install, sealant fasteners. With the fasteners holding it in place. You don't need shop drawings, and they are low cost. The cons are that it burns. It can't be used in types 1 through 4 construction. Here, the insulation's friction fit. They put a little ridge here. To me, that just holds water. If I have an architectural client that's designing a building, he said, "Well, I can use it per code." I said, "Fine, you can use it, but can you please put this vertically instead of horizontally? Because I don't want it trapping water inside the wall. I want the water to get out of the wall." It's not adjustable, and your max spacing is 2 foot. So here's another type of product here. There's more than there's a few out there where you put up a set of a grid of metal tubes. It's metal channels with holes through it. Um, and then you put your attachment rail on that. You run the tubes vertically and put your attachment rail, uh, attach it to the verticals. So few parts, medium cost, fairly low thermal bridging, but you got a lot of screws at 12 inches by 16 inches on center, like quarter-inch screws. It does mechanically fasten the insulation, and you really don't need shop drawings for this. But I don't think it can be used in types 1 through 4 construction because what experts have explained to me is you've now turned the insulation here, which burns, into a load-bearing member. It's going to take the compression wind load of that assembly, so they don't think that it can be used. There's no adjustability in this system. You're going to have to shim every panel. I question the seal at the fasteners here, where I showed you that picture before. Even though it's rigid insulation, you're going to have the same thing. But what bothers me is how are they going to hit every stud every time trying to go through 2 inches of insulation or more and find the studs? It's just not going to happen. And I don't like the corrosion protection on this. It's called ZAM 40, and I'll explain why a little bit later in the presentation. Here's another one just like that, but this one's heavier duty. This can hold a lot heavier panel, and they paint it black, so you can use it with open joint rainscreen panels. So few parts, medium cost, fairly low thermal bridging. You got a lot of screws passing through the insulation. Does mechanically fasten the insulation. You don't need shop drawings on this one, I don't believe. But again, you turn something that, this insulation, something that burns, into a load-bearing member. So I don't think that can be used in type 1 through 4 construction. And I'm not the only one who thinks that. There's no adjustability. Again, I question the seal at the fasteners. And then again, how do you hit the studs every time with a screw through 2 inches or more of insulation? And this one also has that ZAM 40 corrosion protection that I'm not a big fan of at all. Um, there's another system out here. It's got fiberglass clips. You can see these red clips here, and then a Z-furring that's screwed through this. The few parts, low thermal bridging, doesn't need shop drawings. The cost is fairly low, but these fiberglass clips burn. So I don't think you can use that in types 1 through 4 construction. As you can see by the insulation fasteners, it doesn't provide for the fastening of the insulation. The insulation fastener is going to add to the thermal bridging. And you can see here at the bottom of the insulation, you have to cut and fit this around this cladding attachment system, which is going to require a lot of labor. There's no adjustability in this, so you're going to have to shim every panel. And I question the seal at the fasteners. I have a friend that worked for a big company, big engineering company, and they asked him E330 water test on those, and it failed because the backs of these clips are hollow, so they don't recommend using it. So this is probably one of the more popular systems out there. Um, it's clips and metal rail. So it's fairly low thermal bridging, but you do have a chunk of metal, a fairly substantial piece of metal going from the warm side of the insulation to the cold side. So it's going to transmit heat through there. I don't think that these red things are needed. They call, they said, oh, that's what makes it thermally broken. I said, no, it's not thermally broken if a piece of metal goes from the warm side to the cold side of the insulation. And I don't think that's needed. I think that you have a really good thermal break in your sheathing material there to reduce the thermal bridging from the studs to these brackets here. So there's a lot of parts to this. There's a little adjustability on this. You can move this attachment rail in and out a little bit. It doesn't mechanically fasten the continuous insulation. If that rail's pushed back tight to the bracket, yes, it will. But if you adjust it out and that insulation falls an eighth or a quarter inch away from the wall, you get cold air flowing behind it. Your insulation's not doing its job. You have to cut and fit the insulation around the base plates here. Cost is on the higher end here. I question the seal at the fasteners because the backs of these red parts are hollow. I know one consulting engineer makes them set these in a full bed of silicone seal, and because of that concern, it does require shop drawings. And the corrosion protection on this is also that ZAM 40 product that I'll get into a little bit later. So then you have metal clips and rails. There's aluminum or G90 galvanized. They're very corrosion resistant, both of them. There's some adjustability built into these, but as you can see, it's two parts. So you have to do a psi value for the clips or a put for the rail, the attachment rail, and a chi value for the clips. It's a complicated um, um, calculation for that. The costs are high. The aluminum is very high thermal conductance. Like I said, you have to account for both point and linear thermal bridging. It doesn't mechanically fasten the continuous insulation. It'll retain it at the top, but I'd rather see it held on multiple points. And then if you're using the G90 galvanized, they galvanize a whole sheet and then they cut and bend and punch holes through it. So the edges where it's cut, I don't think are protected well. They have an argument for that, but I don't really agree with it. I'll show you that later. And this system does require shop drawings. So I'm seeing more and more of these come out with the stainless steel clip and rail. Um, it's very corrosion resistant. It's low thermal conductance. Stainless is a lot lower conductance value than cold roll steel and much, much lower than aluminum. And it is adjustable. They're starting to build adjustability into it, but it's a high cost. There's a big piece of metal here, and the stainless is very costly. Doesn't mechanically fasten the insulation, so you're gonna have to add the insulation retainers. Requires cutting and fitting of the insulation. They show it here, but you don't, here they just lay it on top of this red piece here. Their thermal isolator, as they call it, but that's going to leave a quarter-inch gap behind your insulation, which you don't want, and it does require shop drawings. Um, this one is aluminum clip and rail system with a thermoclip, they call it. From what the feedback I've gotten, this is the highest cost system available on the market. It is low thermal bridging, and I will give them that this is the only thermally broken system out here on the market. So you have a piece of aluminum, then something here that's a lot less conductive than aluminum. So this is the only one I've seen on the market. But again, it's the highest cost. Um, there is some adjustability in this one, but there's a lot of parts and a lot of screws that get into that. And when I asked their salesperson, I said, "What's your thermoclip made of?" He goes, "Oh, it's polyamide." So you can see here it says polyamide thermal break. Um, if you don't know what polyamide is, you can look it up. I'll show you in a minute. It's nylon. So this doesn't provide for mechanical fastening of the insulation. Their attachment rails can hold it in place. But again, if you adjust it out and there's a half inch, quarter inch gap there, and the insulation can fall away from the wall, then you got your air flowing behind your insulation, circumventing your insulation there. For some reason, they only modeled it with mineral wool on their website, and it does require shop drawings. So again, I did an AI search for polyamide. It is nylon. So extrusion temperatures are 482 to 572 degrees. which, they have to melt it to make that piece. Like I said, your typical building fire is like well over 1,000 degrees. So that's going to melt, which is going to result in panels falling off the building. So their burn temperature is 788 degrees after 842 degrees, but it starts to decompose between 662 to 752 degrees, and then it'll auto ignite at 932 degrees. So you can put some additives in to raise these temperatures or reduce flammability, but they still burn. Lately, newer products of the market has been a slotted Z fairing there. I think that they probably didn't read the definition of continuous insulation. This isn't just a fastener passing through. This is a piece of metal. This one, they have a thermal isolator that clips on the back. But again, you have metal going from the warm side to the cold side of the insulation. This one's new. I guess they just rolled it out, the AIA convention that happened to be in Boston in May. And um, this green piece is their thermal isolator here, which I don't, still you have a piece of metal passing through from the warm side to the cold side. So it's medium cost, non-combustible. There's no adjustability. This one doesn't provide for mechanical fastening insulation. This one does. There's the little prongs that stick up. And like I said, I don't think it complies with the definition of continuous insulation in the IECC. So looking at the rain screed attachment requirements, again, here's my list. And if anybody can come up with anything that should be added to this, please email me. I'd love to hear some feedback from you. But this is the list I used. And when I compared it to them all, I couldn't find any that met all of these for the systems that I just reviewed. So here's my recommendations for specifying a rainscreen cladding system. I don't think you should specify a cladding system that's combustible or has a combustible load-bearing element in any type of construction, even a wood frame building, which says the code says you can. I think these are going to melt before the wood actually collapses within itself. Because if you ever seen a building fire or house fire, everything collapses within itself and ends up in the basement. But I think with these, you'll probably have, or you will have uh, cladding panels falling off the building as the building burns. If you can find ones that mechanically fasten the insulation to avoid the continuous insulation to avoid the thousands of unsealed fastener penetrations to the air barrier, that's better. Make them get 3D modeling done. It's not that expensive. It's only about $5,000, and they will get you the most accurate Chi and Psi values for them, so you can calculate your derating factor of your insulation. And specify cladding attachment system with similar and low PSI or Chi and Psi values. Because if you specify one that's, has a derating factor like zero 0.9 and one that's 0.7, and and then the contractor gets a job and they submit the 0.7, you're going to have to add insulation to that to get to the value you're looking for, the performance requirement for your insulation. And by then it's too late. The building's already drawn. What I found is the systems with point thermal bridges, Chi values, are much more effective than the ones with linear thermal bridges. They have a better derating factor. So that's the end of the technical presentation. So usually when I do this in person, the first question I get is, well, you don't like any of them. What do we do now? What did I do? Well, I invented my own. So, because I didn't like any of them out there. So what I have is a standoff MPV bracket. You can see it right here. It's very low thermal bridging. I built in an inch of adjustability. It is metal all the way through, so it doesn't burn. Few parts, easy to install. One of the most cost-effective systems on the market. I price pointed it for a reason there. You will get the seal at the fasteners to fasten the base plate. It does mechanically fasten the continuous insulation. This is that black disc right there. That's my insulation retainer. So you don't have to cut and fit the insulation around this at all. Cons, we've sold over 100,000 brackets over the last 5 years, and we have not had any complaints on it at all. So here's the brackets. This is what they look like. You have your base plate and your standoff here. And that's going to be the thickness of your insulation. Here's your insulation retainer. Uh, Put that to get it out of my way. And then you have your top plate, which threads into the standoff, and there's 1 inch of adjustability built into that. Um, so these are the various components. And what this is, these threaded parts are called PEM studs, and they actually saved the invention because to weld these in place and get them perfectly perpendicular was really hard to do, and the cost was astronomical. But these PEM studs save the day. It's basically a threaded rivet, and this is what a PEM stud looks like. And these teeth in there grab the plate that it's punched through. In all honesty, I didn't think it was going to work. I thought this would let go, but we were pleased that it didn't. I hired a structural engineer to do the calculations for what I needed, and he said you need for ACM panels, you need a 32-pound gravity load. He said, "Do you want to do different strength brackets for different wind loads?" I go, "No, give me the highest. Go the highest wind loads per the code. I think it's like 135 miles an hour wind load." And I had it calculated for that. Then we prototyped it and brought it to RJ Kenny and Associates and had them load tested. So they put it in the Instron machine and they bent it, the gravity load, and it always fails right. I had them screw it all the way out, thread it all the way out, maximum adjustment, and it always fails right there. So that tells me it doesn't matter how long the standoff is, your failure is always going to be there. Um, and then they pushed on the top plate, and that's when I thought the PEM stud would let go, but it didn't. A 12 gauge plate actually bent, and then they pulled on it also. So, they gave me the charts, and where it starts to flatten out, this is where they consider it a failure. As you can see, all these tests, they never went back down to zero pressure, so it was never tested to failure. It's just where the deformation got to the point where it's unacceptable. And what they came up with was for gravity load is 60 pounds, compression and tension 550 and 550. What does this mean? Well, basically we calculated my engineer wanted 32 pounds. We got 60 on bending, compression and tension. He was looking for 266. We got 550 on it. We're really happy with that. What does this mean for bending? The gravity load, 60 pounds, you can go up to, it fails at 11.25 pounds per square foot of veneer. So we say don't go over 10. If you have something that's more than 10 pounds a square foot, which is like your 2 centimeter granite, you could just double up the spacing on it. I had it engineered to be spaced 1 foot 4 by 4 foot to minimize the amount of metal going through that wall. But you can double up on that. But most of your thin veneers are below this, and your ACMs are like 4.5 pounds. Thin brick are like 8 pounds a square foot. Your fiber cement siding's like 6 pounds a square foot. So most of the materials you're going to clad with thin cladding is going to be under this 10 pounds. So compression for and tension, the 550 pounds converts to a 292.56 mile an hour wind load. The highest wind ever recorded in this country is during a hurricane in the 80s and in Texas, and that was 185 miles, like 180 mile an hour winds. So here's your typical layout. Go 1 foot 4 by 4 foot in spacing for the brackets. So there's one bracket of per 5.32 square foot of wall with just a 3/8 diameter piece of metal poking through it. And for your attachment rails, instead of making it, shipping it all over the country, we decided to go with hat furring because you can buy that at any wallboard supply place. It's shipped in bulk, so I don't have to truck it across the country, and you get your fasteners there also. And you just fasten your veneer panels to that. Some contractors like that, that fastening point at 2 foot for the reveals in their metal panels, and when they want to attach that, instead of doing 2 sets of hat furring or attachment rails like some systems have out there. I said, well, the wind load's all going to be taken by the hat furring and transferred to the bracket, was transferred to the construction to the structure. You can just put a piece of flat stock here and use that to attach to it. For your taller panels, if you want to go 1 foot 4 by 4 foot, put your hat furring attachment rail horizontally at 4 foot. That'll work. I have one contractor out here near me that just loves to have that, they have the Z furring at 2 foot on center, so they want their attachment rail at 2 foot. I go, that's fine if you want to go 2 foot, but you can open up the horizontal spacing now to 2'8" or 32 inches. So you still get that one bracket point per 5.32 square foot of wall. If you go with a real thin metal siding, like they call a single ply, kind of flops in your hands, you can open up that, you can't go more than 16 inches on for the span of that metal, but you can open up the this bracket spacing to 4 foot. So and yep, you can even do thin brick veneer with the system with the brackets, do the bracket, your hat furring, and then attach your trays, your mounting trays to that. Here's a job in Massachusetts that we just finished up a couple of months ago where they had thin brick. This was conventional brick on either side of the opening, and then with the insets they wanted to use thin brick. So we put the brackets up, the attachment rail. Here's the white trays to stick the brick into, and here's the brick installed. He's pointing it up, and this was a job all done. There was a bunch of these setbacks that they used the brackets and the hat furring on. So I did hire RDH to do 3D thermal modeling for that using the Heat 3 version 9.0. Here's the report. They ran through it. They ran the thermal modeling, and they show you this table of in that assembly, depending on your stud spacing, and they want 24, 32, 42, and 48. I said, why? Mine are 16 by 48. They said they wanted to compare it with the other systems. So I don't think these values are really needed. And then they go 2-inch mineral wool, extruded polystyrene, polyiso, 3-inch, 4-inch. But once this code kicked in for derating, I said, wait a minute, I need my chi values for this. And they said, oh, they're in the appendix. So in the report, they give you the chi values to use when you're doing that calculation that I showed you. So we'll go back to that calculation for derating. And so for our point thermal bridges, which the bracket, standoff MPV bracket is, you take the chi value, which is let's go for 3-inch mineral wool. That's really popular uses. The chi value is 0.0409. So we'll use that number in the calculation for our chi value. And we'll take a 20,000 square foot building, 20,000 square foot opaque wall with 3-inch mineral wool, which your R value is 12.9. U factor is 0.0775. So to get the U derated, take that chi value I showed you, 0.0409, times 4,135, which is 20,000 square feet divided by 5.32, the spacing, and then I add back another 10% for top of wall, windows, corners, whatnot. Divided by the 20,000 square feet, add that to your U 0.0775, which is your opaque wall, and your U value bumps up to 0.0859. Your R value goes from 12.9 to 11.64. So you take the U derated less the U opaque, there's your difference, divided by the U opaque. So the difference is an add of 0.084, which is a 10.83% increase in the U factor. If you want to do the devaluing of the R value, you take your original 12.9 minus the 11.64 derated. The difference is 1.26 divided by the original 12.9 is 0.0976, so it's 9.76% decrease. So your derating value is 0.9. Your FRP from the different sites I've looked at, they're claiming 0.92 to 0.95. So we're really close to that with the brackets, and some people don't understand why. And I go, well, because from the same building, you need 10,000 linear feet of this continuous Z-furring, where you only need 4,135 brackets there when you're doing the calculation. So as far as NFPA 285, I know Jess Beidel very well. He actually wrote it. He used to work for Hughes Associates. I had him present at the Air Barrier Association of America annual conference and trade show several times. So I showed him the bracket and I said, what can I do? Do I have to run a $30,000 test? And he said, no, I'll take care. I'll write you a letter. So for the low price of $5,000, he wrote me this letter saying it won't affect it. Here's your typical layout of your bracket with hat furring, attachment rail, and your ACM panel attachment. You can do, I have a couple, my one customer did a mini Z. I don't know why. I'd rather have two legs. It's stronger. And of course, you have an eccentric load on this leg here when you do it. I don't know why they did it. Because of that, they had to close up the spacing to 1 foot 4 by 2 foot, which drove the cost up. And they said, and when I showed them what they could have saved, they were pretty surprised. And they went back to their engineer and said, from now on, I want a hat fairing, not a mini Z. You can do flat stock. I've done one job with that. It has to be pretty heavy gauge. So our standard sizes are for inch and a half, 2, 3, 4, 6, but I have all custom sizes available. You tell me what the thickness of your insulation is. I have a job in fabrication right now. It's 5.5 inches insulation, so I can do any size on that. The finishes I offer are zinc and yellow chromate plating and stainless steel. Why did I do zinc and yellow chromate plating? Because I wanted hot dip, but it wouldn't work. The parts wouldn't screw together after hot dip galvanizing. Ceramic coatings make the bracket more expensive than stainless. So the zinc and yellow chrome plating offered the closest protection to hot dip galvanizing that I could get. And in talking to the American Galvanizing Association, they were telling me the corrosion resistance depends on the concentration of zinc in the coating and the thickness of the coating. That's it. So the hot dip galvanizing has 98% zinc in the coating. This ASTM 154 that's been around longer than I have states this, and it requires 1.5 ounces of zinc coating per square foot of exposed metal, which translates to 2.2 mils of zinc coating or 1.1 mils of coating per side of the component. So um, zinc and yellow chromate under ASTM B633 is 98% zinc, but the highest class that they have, the FE/ZN25, is only 0.98 mils thick per side versus the 1.1, but it's pretty darn close to hot dip galvanizing. Your G90 galvanizing is 98% zinc, but it's only 0.81 mils thick per side. And your G40 or ZAM40, the ZAM40, ZM40 is only 91% zinc. The A that was in there before stands for aluminum. They replaced some zinc with aluminum, and supposedly that makes it last longer than hot dip galvanizing in a brine tank test. But when I talked to the American Galvanizing Association people there, the engineers, they said the brine tank test is not relatable for hours in service at all. They have their own method of measuring, and I'll show you that in a minute, but that's only 0.36 mils per side. So here's the ZAM, like I was telling you. They take some zinc out and add some aluminum, and they've written their own ASTM on this. The ZAM was developed by Nippon Steel and I think 2006 and brought over here, I think in 2015 or 2016, and they wrote an ASTM for it. I asked the American Galvanizing Association what the position on that was, that adding aluminum makes it more resistant to corrosion. They said they had no comment, but this is a table from the American Galvanizers Association. Zinc coatings, a comparative analysis of process and performance, and I'll show you here. This is where we get these numbers. G90, 0.81, G60, 0.54, G40 is 0.36. So what they go by is what's called time to first maintenance. This is their chart. And the time to first maintenance down here is defined as the time to 5% rusting of the steel surface. So in a suburban climate, it's going to take about, and you're 1 mils thick, it's going to take about 25 years to get to 5% rust on the surface. So let's take a look at how that translates out to time to first maintenance. So hot dip galvanizing, you get 25 years times 1.1, you get 27.5 years. Zinc and yellow chromate, 24.5 years. G90 at 0.8 mils is 20.25 years. G40 at 0.36 mils is 9 years. And then because of the reduced zinc content, the ZM40 is 8.36 years. And like I said before, I don't like these plated steel where you cut and punch, because when you cut it, you're going to cut through that zinc plating. And this is what the ZAM people said to me. Oh, when you shear it, you're going to drag some of that galvanizing over the edge, and over time, it's going to migrate down. I don't see how a solid can migrate, and it'll protect itself. The protective film changes from gray to gray black. Now, a lot of the galvanizers that are companies that make galvanized sheet say this too, but I was an expert witness on this one job, 4 years old. Here's the cut edge of flat stock, and that's corrosion. So I don't think that they can make that claim. My packaging, I put it in 5-gallon pails with base and top plates because there's never enough empty 5-gallon pails on a project. The insulation retainers are in a 2.5-gallon pail, and they all have lids, so they can just leave it on the lift at the end of the day. Just put the lid on. They don't have to worry about taking it off the lift. So here's some jobs. Here's a spray foam job where we used them. You can see the brackets on the wall. We didn't need the insulation retainers. Put in the top plate, put your hat furring on, and then attach the siding. This is fiber cement siding. This was the job all done. Here's a job with tall panels. This was the one they used that mini Z, so they had to space it at 2 foot on center here. You can see the mini Z here. But there's that same job. Here's another job. The consultant, because they used a fluid applied air barrier, they don't like that. They made them put a blowout patch of peel and stick over every single one of them. But this was mineral wool. And mineral wool, you just poke it through, and so this again was horizontally with the tall panels on it, and you can see the engagement of the top plate screw in the that furring on there. This one,
Len, can I can I interject? Can we have some time for a few questions?
Sure. I'll just click through. I got like three,
Perfect.
4 or 5 more slides. It's
Awesome.
just
No worries. Take your time.
same school here. Here's one with ACM panels. You can see them here. This one we just did in Arvada, Colorado. It's the first of 6 buildings were specified proprietary. This is the NREL facility, National Renewable Energy Lab, and here's the last one. This is corrugated core 10 steel, weighed 24 pounds per square foot. So we had to tighten up the space in a 16 by 16, but nobody else's system could have held this up. And that is about it. If you have any questions or you want a copy of this presentation, there's my email address at the bottom, and here's our website here. And I am all set if you have any questions, if there's any questions out there.
Okay. I'm going to ask them real quick here for you. Thank you so much for the presentation. I may have missed this, but on residential projects, how do you feel about the plastic furring strips? Often have holes for drainage and can be used vertically or horizontally, about 3/4 of an 1/8 inch thick. How about, say, the Benjamin Opdyke drainage screen wrap, self-adhering under, say, composite siding that looks like wood?
Yeah, that's fine. That's you have your nails going through or your fasteners going through. I know the product. It's called Home Slicker, and that's just to create a vent space behind there. And I've run a bunch. I've actually fixed buildings where they put the siding right up against the water barrier, and they had failure of the sheathing. But that material creates a 1/4 inch drainage and ventilation space. So there's drying potential to that. So that's a good product for that. I wouldn't. You can't hang a rainscreen cladding system like ACM or fiber cement on that. Well, you can put it behind fiber cement as long as you have um, the fasteners going through it, and it's only 3/4 inches thick. If you're going to put a bunch of insulation out there, then I don't think you can rely on that. So
Got it.
next.
Okay, we're going to do one more question and then any other questions can be answered through email. Any thoughts on the drainage mesh matrix, often used under wood shakes, but also under composite or plastic siding?
Yeah, that's that same type of question.
Okay,
The composite drainage materials like the Benjamin Updike Home Slicker, Keen Building Products has the rain screen product out there. There's a bunch of them out there, but same thing. If you
awesome.
if you can put that right over your sheathing and then put your siding on, but if you have insulation to the outside of your sheathing, I think you're going to need um, like one of these rain screen cladding attachment systems, and they will provide you. Most of them do provide you with that ventilation space and drainage.
Awesome. Thank you so much, Len, for that presentation. Any other questions, you'll be able to be in contact with him via email. And I think that's it. Thank you so much.
All right. Thanks, Elisa. Thanks everybody for attending. Appreciate it.
Bye, Len.